Welcome to The Explainer. Today we are diving into something absolutely wild. We're looking at a master plan, a literal roadmap designed to take you from absolute zero to an international level PhD expert in hybrid quantum neural networks. And the crazy part? We're mapping out how to do the whole shebang in just 12 months. So if you're a focused learner looking to compress years of grueling research into one hyper-efficient timeline, you are in exactly the right place.
All right, here's our ultimate chronological blueprint. We're breaking down a one-year research marathon into an actionable, five-phase hero's journey. First, the quantum quest begins. Second, entering the quantum realm. Third, mastering hybrid quantum networks. Fourth, battling adversarial quantum attacks. And finally, becoming a quantum expert. Let's jump right in.
Phase 1. The quantum quest begins, focusing on mathematics and programming. Before we can even think about touching a quantum computer, we absolutely have to build an unbreakable foundation. Think about how this timeline builds a sheer compounding momentum. In months 1 and 2, your focus is exclusively on classical programming and intense mathematics. You're mastering Python, NumPy, and linear algebra. Why? Because that perfectly sets up months 3 and 4, where we finally transition into quantum mechanics and actually start running real quantum circuits on IBM hardware. It's a rapid, calculated escalation. There is a stark, absolute warning from the source material that we really need to heed. Without strong mathematics, quantum mechanics becomes difficult, variational circuits become impossible, and gradient optimization becomes confusing. This isn't just a gentle suggestion, it's a hard prerequisite. If you don't master linear algebra, eigenvalues, and tensor products right out of the gate, those quantum gradients you'll need later, they'll be entirely incomprehensible. So how do you actually absorb all that math and coding in just a few months? Well, you adopt a totally grueling daily schedule. You're starting with math at 6 a.m., so I really hope you like coffee. That moves right into research reading, followed by coding, circuit building, and evening experiments until 9 p.m. This extreme, regimented dedication is literally the secret to compressing a multi-year PhD workload into a single, highly focused year.
Phase 2. Entering the quantum realm, covering foundations and tooling. This is the exact moment our classical training finally meets the quantum world.
To pull this off, you need to acquire a very specific software stack. You're taking your Python and PyTorch knowledge and integrating it directly with Qiskit for quantum circuits and PennyLane for hybrid machine learning. Mastering these tools is what transitions you from just doing theoretical math to practically building fundamental quantum setups like Bell state generators and running complex search algorithms, such as Grover search. And those tools allow you to manipulate mind-bending phenomena like superposition. Now, the equation might sound intimidating, but at its core, it's just a quantum state represented by vectors. Because you already conquered linear algebra in month 1, you can immediately understand the mathematical basis of how quantum operations, like the Hadamard gate, actually function to create these states. Moving on to Phase 3, mastering hybrid quantum networks, where we combine AI and quantum. This is the sweet spot, where we fuse classical machine learning with quantum computing to create something entirely new.
We are now entering a deeply crucial 4-month stretch. There's a massive shift happening here. We're moving away from just learning existing tools and transitioning into conducting actual, bleeding-edge PhD-level research. By month 5, you're encoding data into quantum states, and by month 8, you're building full experimental frameworks to test your very own hypotheses.
A concept you have to master here is variational quantum circuits, or VQCs. These are parameterized circuits optimized using a classical loss function. I really want to emphasize this point. VQCs are the absolute beating heart of hybrid quantum neural networks. They act as the bridge that allows a classical optimizer to successfully train a quantum circuit. But hey, it's definitely not a smooth ride. Welcome to the ultimate boss battle of month 7, the barren plateau problem. As you try to train these hybrid networks, you'll inevitably hit a mathematical wall where the gradient simply vanishes and the variance of the derivative approaches 0. Your training just halts. Overcoming this specific roadblock and finding ways to preserve that gradient, that is exactly what will earn you your PhD. To solve massive problems like the barren plateau, you need a rigid structure. Specifically, an exact step-by-step pipeline for your experimental framework. You load the data set, embed it into a quantum state, pass it through your variational circuit, optimize it, and measure the accuracy. Notice step 5 there, an adversarial module? That happens to be our next major focus. Phase 4. battling adversarial quantum attacks, focusing on security in the NISQ era. We're now shifting heavily into the cybersecurity aspect of this roadmap, because it's not enough to just build a quantum neural network. You have to defend it.
Now begins the rapid sprint to the finish line. In month 9, you are mastering how to mathematically attack your own quantum models using methods like FGSM, the fast gradient sine method. This is a technique designed to fool neural networks with tiny, invisible perturbations. By month 10, you're optimizing for noisy, real-world hardware, which immediately feeds into drafting your research papers and finalizing your thesis chapters in months 11 and 12.
You see, there's a huge difference between standard optimization and robust adversarial optimization. Standard optimization just tries to get the quantum network to function, but robust adversarial optimization, that assumes malicious actors are actively trying to break your model right now. If you want to deploy quantum malware classifiers in the real world where actual digital threats exist, achieving this adversarial robustness is an absolute, non-negotiable necessity. And doing this in the real world means dealing with noise. We're currently in the NISQ era. That stands for Noisy Intermediate Scale Quantum. To run your robust models on actual hardware from IBM or Google, you must utilize specific optimization techniques. You have to mitigate errors, prune your circuits, and heavily reduce your gate counts, or the ambient noise will completely destroy your delicate quantum states.
Finally, Phase 5, becoming a quantum expert through publication and thesis. You've done the math, you've built the hybrid networks, and you've secured them against attacks on real noisy hardware.
The roadmap leaves absolutely zero room for ambiguity here. Quote, you must code daily, read papers daily, write notes daily, implement experiments weekly, publish continuously. There are no shortcuts. Absolute, relentless consistency in these fundamental habits is the only mathematical way to achieve an accelerated 12-month timeline.
Now, when it comes to the thesis itself, the source material systematically breaks down what is usually a terrifying task. It basically transforms an insurmountable mountain of writing into a simple chapter-by-chapter checklist for month 12. If you've been following the experimental framework we discussed earlier, Chapter 3 on methodology and Chapter 4 on experimental design essentially write themselves.
And your goal isn't just to write a thesis that gathers dust on a shelf. The objective is to strategically target specific, high-impact journals. You want to take your hardware-aware optimization findings and your adversarial robustness frameworks and get them published in highly respected venues like IEEE Access and Quantum Machine Intelligence.
If you stick to this grueling, compounding roadmap for exactly 1 year, the payoff is just incredible. We're talking 2 to 4 peer-reviewed publications, a fully completed PhD thesis, real-world hardware experience. You literally transform from a beginner to someone holding international research-level skills in quantum AI and cybersecurity.
We've unpacked the foundational math, the quantum mechanics, the hybrid models, and the adversarial defenses. You now have the exact chronological roadmap to achieve a PhD level of expertise in just 1 year. The path is crystal clear, but the required work is monumental. So, the only question left to ask is, are you ready to build the quantum future?